Nambu, having started it, gets the credit with the Nobel Prize. So we're led from this spontaneous symmetry breaking to the introduction of this mysterious particle called the Higgs, and the experimenters are still at work. The experimenters are now building even bigger machines, such as the Large Hadron Collider at CERN, 27 kilometres around, to try to make this particle, again using Einstein's idea of E equals mc squared, put enough energy together in a collision and you can create the mass of new particles. That's what the LHC is about. And I meant to put a proviso up there. The LHC is starting up. At CERN is starting up. That's indeed true. And we hope it will start up again in a couple of months' time. The detectors to try to catch things like the Higgs have got even bigger. Okay? You've now got the giant, this is just one example, the giant detector, that's an idea of the size of people, to catch the things that come out. The basic idea of this, might take a second to start up, is that you accelerate protons around in one direction in this big accelerator. There they go, getting more and more energy, and off they go eventually. There they go, two lots of protons. One lot you send that way, one lot you send that way. Round and round they go, getting faster and faster. They collide eventually in the middle of this big detector. Okay, the protons are coming together. The energy that they're carrying is turned into the mass of a lot of other particles that spray out and get caught by this big detector. If we do the experiments right, some of the particles that come out may be elusive Higgs bosons. Perhaps we'll see even more interesting things coming out, such as new particles that might have properties that will violate this CP symmetry and might explain to us why Kobayashi and Maskawa's idea gets the evolution of the universe wrong by quite a lot. Okay, so that's what all the hullabaloo is about in the building of the Large Hadron Collider at CERN. So to finish off, I'm going to come back to Paul. And we're going to decide, now that we've understood something about the fact that nature is not quite symmetric between matter and antimatter, the tiny bit of difference between the way that matter behaves and the way that antimatter behaves, and we've seen it in experiments we can do on Earth, and we can think about it in terms of what's happened to the universe. So we could now ask ourselves a question, understanding a little bit about the asymmetry involves reflection in a mirror and turning particles into antiparticles, matter into antimatter. Could we do an experiment, if Paul was sitting off in his distant galaxy, to figure out whether he was made of matter or antimatter, and therefore whether we should go and meet? And the answer is yes. And to give you an example, we can use these funny old kaons that I talked about. These neutral particles, no electric charge, that can be made in an accelerator, sent across the room, falling apart, and we detect what they fall apart into. Those of you who are paying close attention will realise that these long-lived guys fell apart into three other particles called pions. But that's not the only thing they can do. What they like to do best is fall apart to make electrons, neutrinos, and a single one of those other particles called pions. But the funny thing is, because of this asymmetry in the laws of physics, they don't fall apart to make electrons with the same probability as they fall apart to make positrons. It's quite amazing. They don't have an electric charge themselves, but they like to make positrons when they die a little bit more often than they like to make electrons. It's only a small effect. It's about 6 parts in 1,000. So you'll get 1,006, roughly, positrons for every 1,000 electrons if you watch these things decay and have the appropriate particle detector to catch what they do. But that's just enough to answer our question, is Paul matter or antimatter? Because what we do is we send a radio signal over to Paul in his galaxy and we say, Paul, we've got a great experiment for you to do. We want you to make a beam of these things, we call them K-longs. And we want you to build a detector, and we want you to catch the things that decay when these particles die. Now do your experiment carefully and tell us the following thing. You're going to find that you're going to make particles in a magnetic field that bend to the right and particles in a magnetic field that bend to the left. Tell us which ones you catch more of. So you do the experiment and presumably they'll find they catch more of one type. Now, Paul, tell us, what do you call the charge of that one that you get more of? Do you call it an E plus particle or do you call it an E minus particle? So he sends back his radio signal and we look at the results. Paul says, oh, we call them E plus. Great. Get in our spaceship, head off to the other galaxy, and I'm quite happy to shake hands with Paul. He's made of matter. If Paul says, oh, we call them electrons. No way, Jose. So there are very practical applications of these rather esoteric ideas. Okay? That we've met tonight. But I hope I've at least given you a feeling for the quest that's underway to understand the basic building blocks of matter, the forces between them. We've seen how it can lead to a rather simple picture of what those fundamental building blocks are, and it even has implications that determine the ultimate fate of the universe, how it got to be, how it is, and indeed how we are even here at all. I'll leave it there. Thank you.